Should be able to go here. All right, so this is kind of an outline of what we're going to talk about. Actually, and I don't have the first part of this, which has to do with regulation of blood glucose. So we'll talk about some of the metabolism involved in that. And then we'll talk about what normally happens. We'll talk about how beta cells work. And then we'll talk about how we determine if something's not working properly in blood glucose regulation in a person, how we test for that. And then the last part of this, we'll talk about glycemic index of foods, like what that means. So essentially what you guys did today, because you all did the standard, you're simply comparing your blood glucose response to like what we consider kind of normal for 329 students. Remember, there's a lot of variability. But we'll also talk about glycemic index of foods, just in case someone brings in a food, they can actually do some of the calculations to see what a food actually does to the blood glucose response, and that's what glycemic index is. So let's go through this. Let's go to 328 memory lane. Lafrano taught it last quarter. He might do some of this a little bit differently than I do. We use the same textbook. And does this look familiar? I know this is pre-Christmas, right? But this is a summary of carbohydrate digestion. So, for example, if a person consumes something with starch, very common in our food sources, then remember that starch is all glucose, but it has a combination of different molecular structures because of the glycosidic bonds. So as that starch enters into the digestive system, goes through the mouth, right, and you have a little bit of digestion starts, and then it goes into the stomach. There's a tiny bit of digestion there. When it goes into the gut, into the GI, the small intestine, that's when the pancreatic alpha amylase is released, enters into the small intestine, and that's where you start getting the most significant breakdown of starch. You end up with these products initially that are isomaltose, maltose, and maltotriose. All glucose containing, all slightly different molecular structures. So it's not ready for absorption yet. And then on the brush border membrane, you have other enzymes that are involved. You have isomaltase and maltase, which can break down each of those structures to glucose. Does that take a long time? It can happen relatively quickly depending on what else is in the gut. But a lot of times we say, hey, you need to eat complex carbohydrates. Those are the healthy ones. Right? Is starch a complex carbohydrate? It is because of its large size. So we say, oh yeah, that's a complex carb. Eat your pasta, your potatoes, all that kind of stuff, right? And I think what a lot of people don't realize is even starches can cause significant increases in blood glucose, even though they're complex. So we want to be careful about just saying, yeah, eat complex carbohydrates, right? I say this over and over again more and more lately. A person needs to eat what they need. So we need ways of assessing how much of a particular nutrient people need. And carbohydrate, we know, has a lot of bad press right now, right? A lot of people that are talking to you, especially, you'll go, oh, hi, how are you? Nice to meet you. Oh, what do you study? I study nutrition. Oh, I want to talk to you about the keto diet, right? Or whatever. Should I be on it? What should I eat? Should I, right? And then it starts. Well, we want to be able to tell people, well, you got to eat what you need, right? We need carbohydrate. We just want to make sure people eat the right number of calories, the right macronutrients, including the right amount of carbohydrate. So we'll talk a little bit about that as we go. But I'm a proponent of carbohydrates, so you'll be able to tell that immediately. Next one, sucrose. Can anyone think of any food sources that might have some sucrose in there? Right? There's a lot of them. That's sugar. A lot of people get half of their carbohydrate calories from sugar. So that's one we really do want to watch. Now that one, that's a disaccharide, right? Composed of fructose glucose. One enzyme, sucrase, degrades that. And that's on the brush border membrane. So we consume that sugar, goes through the mouth, through the stomach, basically undigested, goes into the small intestine, sucrase on the brush border membrane, liberates fructose and glucose. Next one, lactose. Where do we get most of that? Dairy, right? That's the carbohydrate in dairy. So a variety of different food sources. Lactase is the enzyme that's supposed to convert that, and obviously you guys learned about how it's expressed according to age commonly, and there's genetics involved. But in general, as we get older, we tend to express less and less lactase. And without it, that's what causes lactose intolerance. But lactase is on the brush border membrane, converts lactose to galactose and glucose. And then the last one is maltose, relatively small amounts in the diet. Grains are probably the most significant source of maltose. The enzyme maltase, pretty simple nomenclature there, right? Maltase, converts out to 2 glucose molecules. So over on the right side of this, we have the absorbable forms of carbohydrate, the monosaccharides. Remember, carbohydrates have to go to monosaccharide forms for absorption. Okay? Remember this? Okay. 3 of us do. Cool. So this is an enterocyte. This is a single enterocyte. And enterocytes are the absorptive cells in the gut. And this is showing the brush border membrane on the left and the other membrane on the other side of the cell. What do we tend to call that one? Basolateral. Sometimes referred to as the serosal. This is apical or brush border. This is basolateral. You ever heard that term? Basolateral, B-A-S-O lateral. Okay? 2 plasma membranes. Remember, these are the cells that are basically covering the villi that are making up most of the small intestine. And on the other side of this is what? That's the blood. Specifically portal vein. Right here. Okay, so here are the monosaccharides. Glucose, galactose, and fructose. Glucose and galactose, remember, go through SGLT1. That is an indirect active transporter. And that transport is activated by sodium. Remember, sodium binds conformational chains. That increases the affinity for glucose or galactose. It binds. Sodium goes in. Monosaccharide goes in. Sodium immediately exported through the sodium-potassium pump. Remember that? So sodium is what's driving uptake of glucose and galactose. So anytime we see an active transporter, we can think of things like it's fast, it's specific, it's efficient. Right? And you can go, it's unidirectional. Doesn't matter how much glucose or galactose inside the cell, SGLT1 can still drive more in because it's sodium that's driving it. And the sodium gradient is consistently maintained by that pump. And that's not only in enterocytes, but that's throughout the body. And you don't have to remember this, but just to put some relevance to this, I think about 1/3 of our daily ATP use, sodium-potassium pumps throughout the body. It's that critical to maintain that sodium-potassium gradient. Once glucose, galactose go into the cell, they'll run down their concentration gradient through GLUT2. Remember, GLUT2, the glutes are, what's their mechanism of transport? Active transport? Facilitated-Diffusion, right? So they're gradient dependent. So it's a nice setup because SGLT1 can drive up concentrations of glucose, galactose, and they'll run down their concentration gradient through GLUT2. And they'll go into the blood. Last one here is fructose. Fructose goes through GLUT5. Even though this is called a GLUT, a glucose transporter, this is kind of the black sheep of the family. because it does not transport glucose or galactose. It transports fructose. So when they first started characterizing these guys, they found this protein and went, wow, its amino acids look similar to some of the other glutes we've already characterized. This is the fifth one family member that they started characterizing and go, okay, this protein looks like GLUT4 and GLUT2 and GLUT1 and all those. We'll call it a GLUT. And then later on they went, oops, transports fructose. But we still call it GLUT5. GLUT5 is facilitated diffusion, so when fructose goes in, its concentration goes up. Fructose can go through GLUT2 or back through GLUT5. Right? It's bidirectional, concentration-driven, facilitated diffusion. Have you ever heard anyone say, high fructose corn syrup, things like that bother my gut? Makes me a little bit bloated, I feel a little bit funny. This is why. Because if fructose goes in, if there's too much fructose, the fructose can come back out. So some of that fructose, if a person consumes a significant amount of fructose, not all of it's absorbed. So some of it ends up in the large intestine, and the large intestine love it. They metabolize it. They'll make small little molecules that attract water. Water rushes into the colon, in the lumen of the colon. That's what gives a person that kind of uncomfortable bloating feeling, and it can generate gas. So sometimes you'll get that as well. I think a lot of people eat things and they don't realize it's the fructose that's making them uncomfortable. Sometimes I think people think, oh, I'm gluten sensitive, and they're actually fructose. It's fructose that's doing it. So it depends. I won't go into the gluten thing right now. Okay, and then fructose though can go through GLUT2 and into the blood. So all of these monosaccharides can go through this enterocyte into the blood. And once they get into that circulatory system, they're headed towards the liver. So this is the circulation and extra-intestinal uptake of the monosaccharides. So we were talking about the gut right here. So let's say we consumed carbohydrate, and it went into the enterocytes, and then it went through the enterocytes, and now because it's water soluble, it enters the portal vein. Doesn't go into the lymphatic system. It goes into the portal vein, that's going to the liver. That's a major circulatory system that is draining what's called the splanchnic bed. Have you heard that term? That's all that the blood vessels within the gut. There's a lot of blood that is responsible for absorbing nutrients and also providing nutrients for those enterocytes and other cells. So bottom line is, all those monosaccharides go to the portal vein, they're going to the liver. Right? And the liver absorbs what percent of fructose? Remember that? It's about 100%. 100% of that fructose is going to be taken up and metabolized by the liver. About 100% of the galactose. How much glucose? About 34%. Why is it so much lower? Why does that make sense? Yeah, other parts of the body need that glucose. One thing you should always keep in mind is every cell in the body can derive energy from glucose. That's why sometimes you'll hear people say, oh, it's the preferred fuel source. Every cell in the body can derive energy from glucose. The liver supports a lot of other tissues with its metabolism, including letting a lot of that glucose go so that other tissues can use it for energy. Tissues like the brain, central nervous system, red blood cells rely on glucose exclusively in normal conditions. Is that the same for fat? No. Same for protein? No. Same for ketones? Absolutely not. It's glucose that is the gold standard for energy production in the body. So that glucose goes into the liver cells. Some of it's picked up, some of it goes to circulatory system, goes through the heart, through the pulmonary system, back to the heart, and then systemic. So that glucose, if we were to track it, could do all of that and get to your fingertips in about how long? How long does it take from ingestion to get to your fingertips? Do you have any data that indicates a time frame? Some of you saw it go up 15 minutes, right? So all of that very quickly. So you came in and your blood glucose values were typically between 70 and 110 mg per deciliter. You took that fasting blood glucose value. That's an indicator of how well your body is controlling glucose in a fasting scenario. You haven't eaten carbohydrate for, what, 10, 12, 14 hours. Why wasn't your blood glucose 0 if all of your tissues are using it? What are some of the mechanisms that are keeping blood glucose above 0? 0 is a problem. What are some ways that our body can maintain blood glucose in fasting? What's that? Yeah, glucagon, right? Blood glucose drops, glucagon goes up. Where's glucagon coming from? The pancreas, alpha cells of the pancreas. Glucagon goes up. What does glucagon do? What are 2 things that glucagon does to elevate blood glucose? This is an easy lab, right? You come in, you got to drink that standard, you're sitting here, and I'm asking you a lot of questions. What do you think? How does your body maintain blood glucose in between meals? Hepatic? What does the liver have that helps in this? Glycogen. Remember glycogenolysis? So during fasting, the liver glycogenolysis is elevated. So your liver starts breaking down glycogen and putting glucose into the blood. What's the second thing the liver can do to help increase blood glucose? About gluconeogenesis. Remember that? Gluconeogenesis is also increased during fasting. And that's when the liver cells are taking other substrates, like amino acids and like glycerol, converting it to glucose and secreting into the blood. That's what was maintaining your blood glucose during that fast. Then you come in, you consume that carbohydrate, and the blood glucose goes up. Hepatic glycogenolysis goes down. Gluconeogenesis goes down because blood glucose went up, glucagon went down. Everyone got that? Remember all that? You probably had it in 328, probably physiology as well, right? Some of those classes. And you gotta make sure you have that, make sure you understand that for our quiz in here. And that stuff's gonna be really important for clinical nutrition as you go through that. Because when everything's working properly, the hormones, especially glucagon, insulin, epinephrine, cortisol, those hormones control blood glucose. Every time you eat, those hormones respond. Every time you fast, the hormones respond to try to maintain blood glucose because tissues need glucose. Okay, so now one of the questions is when your blood glucose went up, and now we're at a point where most of your blood glucose is going down, right? Your blood glucose concentration is going down. It's coming out of the blood. Where's it going? Where's most of it going? Muscle. That's where most of that's going to go. And up here I have a table that's an incomplete table. I think there's about 12, at least 12 GLUTs characterized at this point, but the first 7 are fine for us. But these are glucose transporters. They're distributed, boy, on almost every cell in the body, and you can see the list here. The most important ones for us is, again, I want you to remember GLUT2, GLUT4, and GLUT5. GLUT2, GLUT4, and GLUT5, most important ones. We saw GLUT2 on the small intestine cells, on those enterocytes, right? That's the one on the basolateral membrane. But GLUT2 is also in the liver and beta cells. So you want to remember liver, pancreatic beta cells, small intestine have GLUT2. GLUT4 is the next one. And we can just say fat cells, muscle cells, both smooth and striated muscle. So GLUT4 is present on fat cells, muscle cells. GLUT4 responds to insulin. The others do not. Why are we talking about that? Because that's related to type 2 diabetes. And the last one's GLUT5. Remember, GLUT5 transports fructose. It's on intestinal cells. That's it. Good there? So the glucose is going into tissues that have these glucose transporters. Because insulin went up, GLUT4 is activated. So most of that glucose should go into muscle. The next 2 slides, we're going to talk about how beta cells work. You may or may not have seen this diagram. This is a classic drawing of what are called the islets of Langerhans. Have you heard that term? The islets of Langerhans are in the pancreas. And about 2% of the pancreatic volume are endocrine cells. And those are alpha cells and beta cells. So these cells, alpha cells and beta cells, are actually sensing and responding to blood glucose levels. So when glucose goes up in the blood, glucose goes into beta cells and releases insulin. When glucose goes down, alpha cells release glucagon. And what's interesting is they're right next to each other. They have opposing effects, but they are exposed to the same conditions. So now, let's say, for example, we take this beta cell right here, and we look in more detail. So here's a beta cell. This is a pancreatic beta cell. Here's the plasma membrane. And so in your notes, you can say the steps to insulin release. And I'll give you about 5 steps. Step 1, glucose enters through GLUT2 and is phosphorylated by glucokinase. Right, so what does that give us? Glucose what? Glucose 6-phosphate. That's what this is. So glucose enters the beta cell through GLUT2, is phosphorylated by glucokinase. It then undergoes glycolysis and respiration. What's respiration? Right, it's basically, it involves breathing. Right, so a person's respiring, which means they're using oxygen and generating CO2. What metabolic pathways or processes involve that? Yeah, good. Krebs cycle and ETC. Krebs makes CO2, ETC uses oxygen. So this means glycolysis, Krebs cycle, ETC. Right, so the glucose goes in, phosphorylated, metabolized, makes ATP. So its metabolism increases ATP. ATP binds and blocks the ATP-sensitive potassium channel. Pretty good drawing there, right? Little arrow blocking this channel. This channel normally, what's K? That's potassium. So normally this channel is open and potassium is leaking out and maintaining a concentration gradient across this. And what other ion is it balanced with?
Sodium.
Sodium, yeah. So normally sodium is your most significant extracellular cation, and it's balanced with potassium, which is a major intracellular cation. It's why good sources of potassium in the diet, fresh fruits and vegetables, for example, once you process them and open up those cells, your potassium's lost, and it no longer is a good source of potassium. And then on top of that, they'll add sodium to it, right, as part of processing. So now you got an imbalance there. But bottom line is, potassium accumulates in the cell. So ATP blocks calcium export. Potassium blocks potassium export. So potassium accumulates in the cell and depolarizes the membrane. What does that mean? It means you lose the charge differential on that membrane, right? Normally the inside of the cell, slightly negative. Outside, slightly positive. So you have a polarity across a membrane. Another way of saying that is there's a voltage potential across that membrane. Remember all that? And that does things like maintain protein structures, keeps ions where they're supposed to be. As soon as you lose that depolarization, this opens. Depolarization opens the calcium channel. Calcium enters the cell at high levels. The calcium activates proteins. That move. Insulin-containing vesicles. To the plasma membrane for exocytosis. Proteins move insulin-containing vesicles to the plasma membrane for exocytosis. So these little yellow circles, insulin. Now when these vesicles move to the membrane, their membranes fuse and the insulin's dumped into the blood. You guys talked about secretory pathway of proteins in 328, right? Remember that, how it goes through that kind of, it'll go through the RER and then it goes through the Golgi. In this case, what's happening is beta cells are making insulin and leaving them in the cell until calcium goes up. Once calcium goes up, the beta cells dump insulin into the blood. So the advantage of this is it's fast. Right? You guys saw your blood glucose go up, and a few minutes later it goes down. Why? Because insulin was already released. Insulin travels to tissues, stimulates GLUT4, blood glucose enters cells, blood glucose concentration goes down. The beta cells do that to increase the efficiency of this, the speed of this, so it doesn't take very long. That insulin's already packed, ready to go, waiting for the stimulus. Okay? Let me make one point on this. See this diagram? The portal vein is exposed to the liver and the pancreas. This doesn't show it, but the portal vein goes right by the pancreas. So the pancreas gets an early indication of how much carbohydrate you ate before the other tissues. And that's important, right? So you can look at it like, wow, as soon as I eat that, insulin can quickly follow. So when that blood glucose goes up, insulin's released pretty quickly. And now the insulin leaves the pancreas and goes systemic circulation. And that's what's happening here. The insulin's released, goes into the blood. We good there? Questions on that? And now let's follow insulin. So here's a plasma membrane of a cell. Insulin has specific receptors. So insulin binds receptors on the cell surface, and the receptors are activated. And change color. Just kidding, don't write that. They're phosphorylated. Have you ever talked about that signaling? And you don't have to remember these details, but this activation means it's an autophosphorylation event. When insulin binds its receptor, causes a slight change in the structure of its receptor. That receptor has what's called autophosphorylation activity through a tyrosine kinase mechanism. So bottom line is insulin binds, insulin receptors are phosphorylated, and that starts signal transduction. Remember those phosphorylation kinase cascades you probably heard about in other classes where now something's phosphorylated, then it phosphorylates something else, and so all these phosphorylation events are part of the signal transduction. For us, we can say the insulin receptor is activated and start signal transduction. If you've ever seen this, if you ever, like today's Friday, it's Friday night, you don't have anything better to do, look up the insulin receptor signaling pathway. Right, your friends will love it. And you can see there's a huge number of proteins that are activated as part of this process. So some of those proteins stimulate gene expression. They stimulate growth. Remember, insulin's an anabolic hormone. It's a very important anabolic hormone. So we can use our diet to control insulin, to control anabolism, to control things like body composition. Because it helps add muscle, for example. Okay? The other part of this pathway that it's showing is, look what happens. Part of that signaling pathway activates GLUT4. Do I have this here? Yeah. So here's GLUT4. I'll come back to that diagram in a second. But here's what's happening. So let's say this is a cell, basal condition. So in other words, insulin's not at a high level here. The GLUT4 is a protein. It's made from a gene. It generates mRNA from transcription. And then GLUT4 sits in these vesicles. These are Golgi vesicles. And the GLUT4 is in the cytosol waiting essentially for insulin. Once insulin goes up in the blood, binds its receptors, signal transduction, moves those GLUT4 containing vesicles. See the way they're here? Now they're heading towards the membrane. So insulin moves GLUT4 to plasma membranes. And then that GLUT4, which is supposed to be indicated by these little, what are those, like arrowheads or diamonds or whatever. Now they're embedded in the membrane. And now glucose goes into the cell. So another question for you is, what kind of cell is this?
Muscle.
Yeah. It's muscle. And you could figure that out by a couple different ways. One is, I've said most glucose after you eat it tends to go into muscle. The other clue is this. GLUT4 is in fat cells and muscle cells. So that's where a lot of that glucose goes, and that's why. And then once the glucose goes into the cell, it can be utilized immediately, for example, glycolysis, or it can be stored as glycogen. But anyway, bottom line, it's out of the blood. We've now regulated blood glucose concentration. And because of that, glucose is dropping, insulin drops. So you got feedback there. Remember all that? Or is that new? Distant memory, fond memories. Good there? Any questions there? So that's how beta cells work and how they regulate blood glucose. That's when everything's working properly. That's what we're going to talk about now. Sometimes the sensitivity or the effectiveness of insulin is compromised. So for example, when insulin goes up and tissues are no longer responding the way they should, what do we call that? We say it's insulin resistance. Have you ever heard that? That's what that means. That means even though the insulin is present, tissues are resistant to its effects. So think about it in this way. Insulin binds its receptor, is supposed to do these things, but it doesn't. Or it does it at a lower level. So now what happens? Less GLUT4 moves to the membrane, less glucose comes out of the blood, so blood glucose stays high. If blood glucose stays high, what's happening to insulin?
It's increasing.
It stays high. What do we call that in a person that has high glucose and high insulin? They are pre-diabetic. Pre-diabetes in general means high blood glucose, high insulin. So what happens? That continues. Beta cells will continue to release as much insulin as they can. It comes to a point where the beta cells will stop releasing insulin for a variety of reasons. Some of the beta cells become destroyed because of things like lipotoxicity, glucose toxicity. Beta cells can undergo apoptosis, programmed cell death, and beta cells essentially can decrease their function. Now what happens? Now you've got high blood glucose, low insulin. What do we call that? That's diabetes. That's type 2 diabetes. Type 2 diabetes is high blood glucose, low insulin, insulin resistance. Do you give them insulin? Typically not. Sometimes you do, but insulin is not as effective as it should be. So typically you use other medications and diet and exercise to regulate blood glucose. So now let's look at those stats I gave you. I gave you a stat sheet. These are a little bit behind. It takes them a few years in order to come up with this, but look at the stats about diabetes. These are from 2011. This is from the American Diabetes Association. Right, so this is just in the U.S. If you look at this number here, it says total prevalence of diabetes. Total, about 26 million children and adults in the U.S., about 8.3% of the population have diabetes. I know at this point that percentage is close to 10. So rather than 26 million, it's over 30 million now. How many people live in the U.S.? You can do that math real quick. What's the U.S. population? What's the population in California? How many of you guys from California? What's our population? It's probably 38 million, 39 million, close to 40 million people. Think about all the people in California. All right, we're more than 10% of the population of the U.S. Now look at these numbers. These are people with diabetes, diagnosed. According to this, 18.8 million people. That number's a lot higher now. Undiagnosed, 7 million people. Right, so you can add those in. They're diabetic. They just haven't been clinically characterized as diabetic. Look at prediabetes, 79 million people. This number right now, close to 100 million people. Right now in 2019. Right? That's almost 3 times the population of California. In the US right now, pre-diabetic. A lot of them don't know. How do you know if you're pre-diabetic? A few different ways. Yeah, measure your blood glucose. Before you came here today, how many of you had done that? Okay. 2 of us. We're nutrition. We're all nutrition majors, right? We gotta do stuff like that. A few things you should know in life. Fasting blood glucose. Your lipid values, cholesterol, HDL, LDL cholesterol, your blood pressure, your body composition, your bone density, your favorite color, your favorite food, all these important things in life. And a lot of people don't know. How many of you think your parents know their fasting blood glucose concentrations? Okay? I would encourage you, please tell your parents, go in, have a lipid panel done, have blood glucose done. There's a few other things I'll tell you that they need to get done. Yes, it's okay to nag your parents. They need these values. If they don't know and their blood glucose is high, they could be pre-diabetic. Tell your aunts, your uncles, your grandparents, everybody that you know, especially there's an increased risk as we get older, but also your other friends. Everybody should know this. The sooner that a person knows they're having issues, the easier it is to try to reverse those effects. If they go from pre-diabetes to diabetes, that's very, very difficult to change. At that point, sometimes, like we're starting a type 2 diabetes project, hopefully in February. We're going to bring in people that are diabetic. We're going to compare them to non-diabetics, and we have an exercise nutrition regimen that we're going to put them through. And we're going to do that for about 4 months, and then we're going to compare health effects. At that point, it's possible that the best you can do for someone with diabetes is decrease their meds, increase their health. They may never have insulin production back to normal again. So it can turn into a lifelong issue where multiple times every day they're doing what you did today. They're doing finger pricks, they're measuring their glucose, they're doing all of that. And that's not fun. And I have friends right now, especially that are older, that you hate to see it. But then I'll tell, like, family or friends will ask me, oh, you know, my blood glucose is high, what should I do? And I'll say, well, you should panic now. You should do everything you can to stop it. If you don't, I can promise you in 1 to 2 years you'll be diabetic. And so far, every time I'm at 100%. Every person that hears that but doesn't do anything about it, they're diabetic. And so we need to know this, and we need to be able to get the word out and try to promote this to people. This is all part of the prevention, and the numbers are staggering, and they're still going the wrong direction. So if you guys stay in nutrition for a while, or if you end up in nursing or anything healthcare related, this is going to be around for a long time, and it's something that we need to try to figure out ways to help people earlier on so that they realize this. Now, it doesn't mean that if a person is diabetic, it means that it's just something that they have to deal with. And if they do all the things that they should, they can live a long, healthy life. It's just harder, but it's worth it. Especially for us, you know, we need to try to establish healthy things with our diet and exercise, and other people do as well. So what are some of the factors that decrease insulin sensitivity? I told you one of them right now, and that's age. So aging tends to increase insulin resistance. Right? That's another way of saying decreased insulin sensitivity is insulin resistance. So aging tends to increase insulin resistance. What else? What do we say is number one of the most significant risk factors for type 2 diabetes? Diet and obesity, right? So obesity, and I'll tell you why. And there's lots to this, but really simply put, obesity is a problem because adipose tissue can become dysfunctional and release molecules into the blood that short-circuit insulin signaling in muscle cells. So you could say significant amounts of adipose tissue increase the likelihood that adipose tissue will decrease insulin signaling in muscle. Sure. Significant adipose tissue increases the likelihood that the adipose tissue will release molecules that decrease insulin signaling in muscle. And we don't have time to go through it in this class, but what that means is there are actually receptors on these muscle cells that will respond to some of those molecules being released from fat cells. And fat cells are good when they're functioning normally. But when you have too much adipose tissue, it causes problems in that adipose tissue so it doesn't work the way that it should. It establishes inflammation, hypotoxicity, all types of things that now cause a response that goes into the blood and muscle cells are affected. That's called tissue crosstalk, for example. And so that's when it really becomes a problem. And that's why obesity is one of the issues. And why is aging and obesity kind of related? Sometimes our lifestyle changes as we get older. We exercise less, we add more fat tissue. And all of those things are kind of involved in this. Another thing that can cause insulin resistance, lack of physical activity. And we'll talk a little bit about diet in a minute. Right, so those are the basics of all of this. We went through that. So let's talk about this. Prevalence in diabetes, pre-diabetes. You guys have the numbers there. We just went through that. In general, normal fasting blood glucose levels are considered 70 to 110 mg per deciliter. That's what they should be. So how do you tell if a person is pre-diabetic or insulin resistant? Well, you can do fasting blood glucose values like you guys did. Person wakes up in the morning, they have a glucose meter, they have glucose strips. They take their fasting value. A fasting value above 140 mg per deciliter on multiple occasions, that's really important, may indicate diabetes. Oh, the other thing that I've added to that study is sleep data. Probably because I don't sleep very much. Sleep is really, really important for regulating blood glucose. And that's why, let's say, for example, a person's fighting a cold, they have something going on, stress, lack of sleep. They might wake up one morning, it might be above that. So we want it to be several times. We don't want them to go, oh, I'm diabetic, it was 140. Maybe not. They want to repeat it. Fasting value between 110 and 126 indicates impaired tolerance. What does that mean? Pre-diabetic. That means they have impaired tolerance or decreased tolerance to to regulating glucose. See the way those are different? 110. So that's a slight elevation. Again, multiple occasions.
Sorry, can I have a test strip,
Sure.
please?
Good. Right? That's one way, fasting blood glucose. Another way, oral glucose tolerance test. That's essentially what you guys did. You fast, take fasting blood glucose, take a glucose load. And that's usually 50 to 100 grams. I mentioned this before. Pregnant women do it with 75 to 100 grams. And that's to screen for gestational diabetes. And then the blood glucose response measured over time. Sometimes you'll do 2 hours, sometimes you'll do 3 hours. They're essentially just looking for that glucose to come down. They're looking for an effective insulin. So let's say today, after 2 hours, your blood glucose didn't come all the way down back down to fasting. As long as the shape of that curve is showing an insulin response, you're typically fine. So I'm happy to look at that stuff for you. Here's some important stuff here. Why are we concerned with that? Why do we regulate blood glucose? Because it can damage other molecules. So how can high blood glucose be harmful? I'll give you a couple different reasons. One is high blood glucose can bind to and alter LDL molecules. High glucose can bind to and alter LDL molecules and increase their likelihood of being part of atherosclerosis. Increase their likelihood towards atherosclerosis. Remember that? You guys learned about that, where macrophages actually target altered LDL, including those that are glycosylated. So that LDL, if it's bound to glucose, can be targeted by macrophage in the intimal layer of coronary arteries, and that can contribute to plaque formation. Another thing that it can do is the glucose can bind proteins and compromise microcapillary, compromise microcapillary structure. Can compromise microcapillary structure. Right? In tissues like what? Kidneys, the eyes, and the extremities. Right? I think we've probably all heard that, right? I'd say, long-term uncontrolled blood glucose levels increases the risk of blindness, kidney dysfunction, and amputations. So even if a person is diabetic, they just got to regulate their blood glucose. I've had people in my family haven't done that, and it's been really, really problematic in those things I just mentioned. Okay? So what are some things that we can do to kind of regulate blood glucose? Just about a couple minutes on this. This is a glycemic index. And I'll tell you what it is right now. And this part of this definition is in that the article that I gave you. Glycemic index is a ranking of dietary carbohydrates on a scale from 0 to 100. Glycemic index is a ranking of dietary carbohydrates on a scale from 0 to 100 according to the extent they raise blood glucose levels after eating. According to the extent they raise blood glucose levels after eating. Sure. The GI, the glycemic index, is a ranking of dietary carbohydrates on a scale from 0 to 100 according to the extent to which they raise blood glucose after eating. Here's the important part. It is relative to a standard. So in other words, you eat a food, measure blood glucose response, compare that to a standard. What's the typical standard used? Glucose solution, like you guys drank. Another standard, white bread. That article mentioned that. More commonly, it's the glucose standard. Nothing raises blood glucose more than that in general. So GIs are always below that number. So we'll look at that in a second. Why was it developed? To help diabetics control blood glucose. So is it useful? It can be in certain situations. What are the shortfalls? Right, so this has to do with food. And so when you look at the glycemic index of a food, it's just for that single food. So shortfalls is, we normally consume meals with several foods. So it's hard to predict single foods will do to a person's blood glucose, right? Because we often eat it in meals. And the way that it's calculated is essentially testing. So it's been a few years ago now, but a few years ago I designed some sports drink formulas, and we wanted to know the GI of that. So we had students come in here, nutrition majors, and I paid them to come into the lab and do just what you guys did. They came in and drank the standard and did the blood glucose response. They did that 3 times. On a 4th day of testing, they drank the sports drink. So this is important. This is how you do these tests. A person drinks the standard 3 times, calculates an average response to the standard. This is just what you guys did on that table that you made, right? And then your next test is the test food. In this case, it was a drink. And you only have to do that one time, and then you compare the response. And this is what it looks like. So in other words, everybody's their own control. So if you look at it here, for example, here's a standard. Let's say they did the standard 3 times. They come up with this curve, and they calculate the area under the curve. The test food day, for us, we did a sports drink, but in this case, they said lentils. Now they eat the amount of lentils that will give them 50 grams of glycemic carbohydrate, and then they do the area. The area of this curve is 40% the size of the standard. So the GI is 40. It's pretty simple, right? Not fun. I mean, hats off to the students that did that. I think I had about 12 students do it. It was right around finals. And they went through it and we got all that data from them. And then there's lots of tables like this. Have you guys ever seen these? So you see these tables that are glycemic index of foods, and how do they do these? It's lab tests. So some labs, that's what they do. Companies pay them and say, hey, we developed a new type of rice, and we think it has a low glycemic index. Will you test it? Well, they have people come in, they pay them, and they do this. But you can see, for example, some of this makes sense. You have brown rice, 55, white short grains higher. That makes sense, right? But some of these don't. Look at spaghetti. Say, hey, eat spaghetti. It's a complex carb. Look how low it is. And yet rice is higher than that. So some of these don't make sense. But if you look at all of these, there's these big tables. I've got an article if you guys want to look at. It's got about 50 pages of glycemic index values. If we look at something like this, you got to be careful if somebody just says, yeah, eat a low glycemic index diet. You can kind of cheat on this thing. Coke, not a real high GI. Gatorade's higher than that. But if you look at some of these, where's the other one? Oh, down here. Jelly beans, really high. Chocolate, lower. That's good, right? And then the next one, I think there's one with ice cream I think I had on there. So one thing to keep in mind, if something has, oh, here's ice cream, 61, that's not a high GI. That's in the middle range. So here's one thing to keep in mind. Does fructose increase blood glucose? If I consume just fructose, does it increase blood glucose? A little bit. Liver converts a little bit, right? But not much. So if you eat something that has a lot of sugar, it might not be a high GI food because of all that fructose. Is it healthy? No, but it's not a high GI. So let me just one more point. Is it healthy to consistently eat a low GI diet? What do you think? So in general, should we try to eat foods that don't cause big increases in our blood glucose throughout the day? Yes. I'd say that the data is pointed in that direction, where it's healthier to eat lower GI foods. And a couple of reasons. It looks like it might be protective against diabetes and obesity, which sometimes go hand in hand. It may also decrease the risk of cardiovascular disease. So we can do things like eat mixed meals, right? Eat fiber. Fiber decreases that response. A long time ago, I used to have the students that were drinking the standard. I'd have a few of them mix theirs. I'd have a blender in here, and we'd mix it with psyllium husk. That fiber, which is a really soluble fiber. And that group, their blood glucose response to that standard was blunted by the fiber. And it's a good example. It got me in trouble. I didn't win any popularity contests because of that. But it shows you if you eat a meal and you're mixing it with like protein and lipids, and those affect the blood glucose response, and so does fiber. So that's a good example of things that we can do. Now there's one exception that I would say is a good time to eat something that drives up blood glucose significantly. When would that be? Post-exercise. Post-exercise is an exception, and in general it's good to eat carbohydrate that causes an increase in blood glucose. That helps recovery. It helps change the hormone profile so that it'll help the benefits of that exercise. Good there? Any questions? Okay, guys, so you should be done, right? Okay. So, clean up. So what you're going to do, before you start moving around too much, let me run through this real quick, right? The first thing to do would be obviously make sure everything that should be in that biohazard bag is in there. Take your lancet, that goes into the sharps. The sharps containers. Everything else with blood goes in that biohazard bag. Then take that Ziploc bag and put it in this red receptacle right over here. Okay? Everything like that goes in there. And then what you're going to do is you're going to put gloves on. Keep your glasses and coat on. There should be lab gloves, or I'll get you some. Make sure your gloves don't have any holes in them, so put a little bit of air in there and check them, put them on. And then what you're going to do is clear your bench top with your whatever, your glucose meter and all that. And then take that Cavicide, liberally spray it so that that whole area around you is wet. So it should be visibly wet. Take a Kim wipe, and remember you got gloves on, move it around so that every part of the bench top is exposed to the Cavicide. Leave it on for 3 to 5 minutes. So we want at least 3 minutes of contact time. Leave that on there, and then wipe it off, and also wipe off the end of your lancing device, right, that was in contact with your finger. Because if I do a finger prick, and then I come back and do it again, it's potentially, there's traces amount of blood on your finger that you now have on the outside of that lancing device. Good there, and then take the tape, the label off your lancing device, and then put everything else back on the bench top. Not up here, not on the shelf, on the bench top. Any questions on that? Okay, if you have any questions, let me know. And then your lab coats, if you want, you can store them here, I think. And then you're good to go. All right, thank you guys. Yes.
How do I take this out?
There's a little lever. If that bottom lever, if you push that up, you don't have to. So you can hold it right above that and use that bottom lever to push it off of there.
That didn't work. It didn't go. I just wasn't pushing hard enough.
Okay, guys, to get the lancet out of there, you can hold it above the sharps container. Hold your lancing device above the sharps container. There's a little lever or button on the bottom part. So it's below the spring button. And if you push that button all the way down, it'll pop that lancet out. Better just leave them right there if you would. Clean off and then put it back there. And then, yes, please. I'll get gloves for you guys. If you don't have gloves in your drawers, I'll give you some
Oh,
gloves.
did
right
you
here.
look? Do we not have any? Here. Ollie.
Those are XLs. There's extra small here, there's mediums here. There's small here and there's larges here.
Strips.
Okay, you can just set them right there is fine. Thank you.